All right, so just to capture for the record, since I am recording this, this is office hours on Tuesday, January 16th, 2023 for CPSC 416 at the University of British Columbia. My name is Tony Mason. I am the instructor, and I don't actually know if anybody is going to come to these office hours, so I'm going to pause the recording. Hopefully I'll remember to turn it back on when that's done, and I will make the recording available to anybody who wasn't able to make it to office hours. So those are the preliminaries. All right, so right now there's nobody here, which is fine. I'll just take this opportunity then to wonder why the picture's blurry, but also to just address general questions, or I get to talk about the class a little bit. So let's see, again, my name is Tony Mason. I'm the instructor of record for the course. This is the first time I have taught this particular course, although it is not the first time I taught a course about distributed systems. I would actually say I think the first time I taught a course about distributed systems was in 1992, maybe. And that was part of something called the distributed computing environment. At the time, this is the early 1990s, there were not a lot of broad scale infrastructural components and pieces and whatnot that tried to use distributed system services. So the distributed computing environment was a multi-company effort to build such a framework. And it was overseen by what is currently called the Open Group, but was previously known as the Open Software Foundation, OSF. The participants in that are kind of interesting. So originally the participants included Apollo Computer, which very early on was acquired by Hewlett-Packard. It included Digital Equipment Corporation, which since has been acquired by Compaq Computer, which was then acquired by Hewlett-Packard. Siemens was involved. Siemens provided an X500 naming service component. Microsoft was involved. Microsoft provided support for diskless workstations, believe it or not. I worked for a company called Transarc, and Transarc's contribution was the distributed file system components, and then actually included both a local file system component as well as a distributed file system component that was in turn based on the work that we had done productizing the Andrew file system into a product called AFS 3.0, and then we were building what was called the distributed file system, or DFS. What did DCE provide? DCE provided threads. So in fact, that was one of the things that HP contributed, was a threading model that was developed at the same time that the pthread specification was being developed. So in essence, we ended up having pthreads implementations. So we were pretty much the first people to start using pthreads, which if you are studying Unix or Linux threading at this point, you will have used pthreads. At that time, almost no one actually had kernel level threading. So there was no distinction between a process and a thread at the kernel level in most of the operating systems. IBM was involved in this project as well, and I'm trying to remember what exactly they contributed. It might have been the Kerberos implementation. I don't recall precisely. It was an interesting project. So so we had threading, we had a remote procedure call. Presumably you've discussed remote procedure call in other courses, probably in 317, or if you took a different computer networking course. The model of remote procedure call is one that was, developed many, many years before that. I worked for a guy who did his PhD actually in performance optimizations of remote procedure calls in local area networks, and he went on to found the company I was working for at the time, Transarc. Then after that, he went to IBM because IBM bought Transarc out. He went to IBM, and then he left there and he went to Google for many years and ran an the advanced research group there. And then he went to a company called 2 Sigma, which does algorithmic trading, high frequency trading. And then he's off doing something else now as well. So RPC's been around a long time at any rate, longer than I've been working in this field. And so the basic premise, the function of RPC really was to allow us to take programs that had a modular decomposition that would allow us to perform some of the functionality via a network call. So you bundle up all the arguments and you send it across. And as you recall, in the last lecture, I was talking specifically about this idea of presentation layer. And so RPC, both there are other RPCs. There's Google has their own RPC now called gRPC, and at the time, Sun Microsystems had something called Sun RPC, and eventually they changed the name to ONC, the Open Network Consortium or something. I don't even remember what the acronym stands for exactly. ONC RPC, which was just Sun RPC under a different guise. The DCE RPC was actually developed by Apollo Computer. And when HP acquired Apollo Computer, the people who had been working on DCE or on Apollo's RPC ended up working on the version that turned into DCE RPC. DCE RPC is still actively used. One of the reasons I mentioned Microsoft's connection, it was very tangential. This just diskless workstation support was because they actually added sorry, watching for Piazza messages, and there's one, but it's not for this. So DCE RPC actually was there in the DCE project itself. Microsoft was working on this diskless workstation support, and as part of that, Microsoft got a license to use DCE RPC. The strange thing is I'm trying to recall who worked on what. I think that actually it was Digital Equipment that ended up building the replacement IDL compiler, interface definition language. So the idea was you would define what the interface, so what does the procedure call look like? And from that, it would then generate code that would bundle up all of the work necessary to perform the remote procedure call. That was really one of the key benefits to using RPC, is that it allowed you to automate the process of constructing language bindings. Today, this is pretty much assumed technology. When you actually look at REST APIs, for example, they have there's a W3C definition. There's a whole mechanism for describing these RPCs, and then the creation of bindings in various languages is pretty much generally automated. And so this is not a cutting edge researchy kind of thing like it would have been 25 years ago. This is just sort of assumed technology, but at the time, it was not something that many people used or employed. So we had threading, we had RPC. RPC in this case actually provided distinct services. It provided the remote procedure call functionality. It provided integration with the naming system, which was not tied to RPC per se, but you still have to have some sort of a naming disambiguation. And that was like what we talked about last week, where I was talking specifically about the domain name system. Well, this was similar, but not exactly the same. We still have a domain name system, but instead this was, how do I bind to a given interface by knowing what the service is that I'm trying to talk to, but not necessarily knowing where it's implemented or precisely how it's implemented. And so it enabled us to ask and to say, okay, here's the service I need. Sun had a thing called a port mapper um, that would do this for you. You'd say, I'm looking for this service, and it would tell you what port to talk to, what TCP port or UDP port to talk to in order to find the service that was actually providing that. And the DCE-RPC had a similar sort of interface, but not only would did it bind to port, but it actually bound specifically to services and versioning. Part of one of the things I mentioned last week that we did, and this is something Apollo had done already. All the DCE project did was pin something down for the DCE implementation, and that was a universally unique identifier. So one of the problems in creating identifiers like port numbers is that if we want to have a well-known port number, then we need to have a central authority to control the allocation of those things. Or alternatively, we need space that is so sparse that it is unlikely we are ever going to collide. And so what they had decided was, they said, you know what we can do is we can use something that's unique to the machine. And they picked the and there are multiple algorithms for generating these UUIDs now, but this was the algorithm that they picked for the DCE. And that was, they would use a 6-byte identifier from the machine. That was the MAC address of at least one of the network controllers on the device. And they would use that to disambiguate in a way that would allow distributed creation of these UUIDs. And so the benefit of that approach was, it meant that I could sit here and generate UUIDs, and I wouldn't collide with any UUIDs that you generated. Now it's a large space. It is a 16-bit space. So it is absolutely vast. You can essentially, I'm pulling it out of the air right now. I don't remember the exact number, but as I recall, there was you could essentially assign a UUID to every subatomic particle and never need to reuse it. There was also a timestamp in there, and there were other bits that included structured or unstructured information. I'm not going to go into the details because it's not super important to the conversation, but it's instead trying to provide you with some of the background here. So we had naming, we had RPC, we had threading. Oh, right, I should probably mention security. So one of the things that we had integrated into AFS, because it was present in the Andrew file system as well, was an implementation of Kerberos. Now, one of the big changes when we went from AFS to DCE DFS is we moved from Kerberos version 4 to Kerberos version 5. If you're not familiar with Kerberos, Kerberos is a project that was done at MIT as part of Project Athena, and it was specifically designed to allow for, I probably should have put the link in the in the post that I had on Piazza. I'm going to actually need to do that. Let's see. So I'm editing it in right now, even as we speak. And since I've got it set for Markdown, I have to put it in parentheses and brackets and whatnot. So there it is. It's actually there. So we moved to Kerberos version 5 at Project Athena. It is an authentication mechanism. It's a zero knowledge proof authentication mechanism. It was already fairly complicated by that time, and that's 30 years ago. It's more complicated now in many ways that we've found holes, bugs, things that we've had to fix because it is extremely difficult. It is one of those things that you will learn if you haven't already, and that is if someone tells you they're going to roll their own security, you need to run from the project. You need to run far, far away because the it's hard. It's very difficult to build that. Sorry, turn my phone up so I can see what time it is because the clock is covered by the Zoom window. Too many distractions in life. But Kerberos does a pretty good job of it. And all these pieces together. So Kerberos actually integrated with the RPC as well. This is one of the things that actually did distinguish it from ONC RPC. ONC didn't actually have any kind of authentication mechanism. At Transarc, what we were doing was basically taking all of these different services and then turning them into something that would allow you to have a distributed file system. And just like AFS, DCE-DFS was a globally distributed file system. The idea was that you could actually have different organizations sharing data across trust domains, and Kerberos supported that. One of the reasons we went to Kerberos version 5 is it allowed a model for delegation, and there were definitely wins that we had for using delegation, performance optimizations. The file system project included a decision by the development team, of which I was a member, that we were going to build a new physical media file system, which in 1990 didn't seem like an outlandish idea, although we definitely spent a lot of time looking at other ways of doing this, and ultimately concluded that if we wanted the functionality, we would need to actually augment an existing file system infrastructure to do this in a way that supported the additional functionality of DCE-DFS. I mentioned one of those pieces of functionality in the course, and that was the ability to withstand server reboots without losing client files. And this is one of these very, very minor details that turns out to be a big deal. In a distributed file system like NFS, for example, they tried to make Unix semantics work correctly. And in Unix, you can actually open a file and then you can unlink the file. And unlink in Unix means remove it from the directory. So there are no references from any directory entry there are no references from this directory entry to this file anymore. And if that's the last directory entry that referenced it, which was pretty common, then what you're doing is you're actually deleting the file itself. So this is a pretty big deal, because what this means is that now the file is open, but we don't have any way of finding it anymore. And so how do we protect ourselves against reboot events? Well, normally what would happen is the file would get lost. I mean, the most common solution here was the file would get lost, and periodically it would run a tool that would find it and recover its space. The difficulty is that when you get into a distributed environment, and this is where the whole promise of RPC, making things transparent and whatnot, you can see it kind of cracks around the edges. And that was because if the distributed file system, if the server had an unlinked file and it crashed, the client no longer had any way of actually opening and accessing that file. And so, for example, in NFS, the way they worked around this is rather than unlinking the file, they would rename it to .nfs and some long identifier. I'm pretty sure the identifier would have had structure, but the point was the file itself didn't really get deleted. So now you, instead of losing the space, you ended up with these phantom files you wouldn't normally see with an LS because they started with a dot. And the ls command would strip out those files, but they were still there. And that was kind of the ugly workaround for that particular problem. So instead, what we had done is in DCEDFS, in the physical file system, we actually would keep track of those files. And we would then, after a restart of the file system, we would then, for a period of time, allow the client to reconnect and re-access those files, even though they were unlinked. So we essentially created um, we called it the zero link count file list, actually. And it provided us with much cleaner semantics. We thought so at the time, that it was important. We could actually reclaim the space for those files. This is a time when the largest drives that we were buying were 1 gigabyte. Those were expensive, high-end hard drives. It was much more common for file server hard drives to be smaller than that, because the half gigabyte drives were much cheaper. And I still remember this because at the time, I was actively involved in the building of this new physical media file system, and one of the things that we discussed was, what's our target size? See, the issue is that if we actually say, okay, we're going to use these really large sizes, then we need to allocate space to describe them, and that space is now a precious commodity. So you try to limit things, you try to make decisions that make sense at the time. And basically our design point was, okay, well, let's do 3 orders of magnitude. So let's do a terabyte instead of a gigabyte. Turns out that was probably not an unreasonable choice. We now have multi-terabyte drives. We actually could support more than multi-terabytes, but we chose numbers that would have required playing some tricks to get things that are larger. Other file systems at the time period did similar things, because space was a finite commodity and we had to deal with it. So at any rate, I'm working on the local file system part. One of the key features that we decided to integrate into the local file system at that point was, in fact, a journal. We decided to use a journaling technique. There were journaling file systems. We were working very closely with the IBM team, because we were building our file system on the IBM AIX operating system platform. So we were working very closely with the IBM team in Austin, Texas, and they had a journaling file system. One of the reasons we chose not to use their journaling file system was because at the time it was actually tied specifically to AIX hardware. We were not able to actually do anything. We couldn't port it to any other platforms, and we had to port it to other platforms. We had to make it work on OSF Unix, which the OSF had their own Unix version that was a mock microkernel-based operating system. So ancient times, for sure. And so we bit the bullet, and of course Transarc was interested in supporting platforms other than just AIX. We ended up supporting a number of different platforms. In fact, at one point I ported our file system, our physical file system, because we needed that in order to get all the functionality of the distributed file system on top of it. I ported that to HPUX in a remarkable 10 days. I went from having nothing to having everything wired into an HPUX kernel. It was quite a hack. Actually, it worked surprisingly well. It was very stable. And some of that was just because the interface for what they had available in HPUX, the VFS interface, matched very closely to what we had used as well, because we were using a very Sun OS style VFS interface, and that was what HP had done as well. Although they didn't have a VFS interface per se, they still had they had a hardwired switch table. So I was modifying an HPUX kernel to call into our file system. Be that as it may, it doesn't make too much difference, but it's kind of giving you some of the context of my own, a little more into my own distributed OS background and where I come from. So I didn't just do the physical media file system. I did do the transactional log for that. And I worked very closely with a guy who was, we had two groups at Transarc. Transarc was a startup company. We had two groups. I worked in the file systems group. There was a much larger group that was doing online transaction processing. They had taken a project called Camelot from Carnegie Mellon University, and they had uh, they were productizing that into something they called Encina. Encina then ultimately gave us something called Corba, which if you have worked in the field for a while, you will probably recognize that name because Corba was kind of a predecessor to much of what we do on the web now with REST APIs, SOAP APIs before that. Corba was older than either one of those. Mike Young, who was doing the transactional system for Encina, and I spent a lot of time talking to him about what good approaches were there, what they had done, various trade-offs, and it was fun because we were able to jettison a large number of the difficult problems that happen when you build a general purpose log for a database system. In their case, it was a distributed database system, but it was still a database system. And I had to worry about many of the same issues that we're going to be talking about over and over and over again. Atomicity, consistency, isolation, durability. I often say I have spent my career in building software in many ways, looking at how you can be a little more flexible about some of those things. So for example, with consistency, in a physical media file system like that, I mean, there's this kind of half tongue-in-cheek joke by the physical media file systems folks that we don't care about user data. And actually turns out there's a certain amount of truth to that. We actually want to get the user data back, but the primary concern of the file system is to maintain the metadata of the file system itself so that it's always in a consistent or coherent state. My job was to build a transactional system that could allow us to log the current state in such a way that we could recover to a consistent state. Now, here's the thing I learned when I did that. I got to define the transactional system. I built a transactional system. You started a transaction. That's great. You then performed a series of distinct operations. Now, as a very classical kind of transactional log, except for the decision to use old value, new value logging rather than new value only. So in new value only logging, I only say, I'm replacing this region of this block of metadata with this new piece of data. In an old value, new value log, you say, I'm replacing this old piece of data, and I literally would copy that old piece of data in with this new piece of data from this place in this data structure. And you go, well, that seems kind of inefficient. And in some ways it was inefficient, but it turns out that one of the benefits of that was that it allowed us to safely write metadata, in-memory metadata, with changes that had not yet been committed in the log, as long as the log record that recorded the update had already been safely committed to the disk. So it freed some of it gave us some flexibility, freed some of our ability to handle the pinning things down in memory, because as long as something has a dirty change in memory that hasn't been committed to the log in a new value only system, you can't write that. So this gave me a little more freedom, a little more flexibility. It was interesting. It was a more complicated log than what you generally see, but it was an interesting approach to it, and it worked out. It worked out really well. So I learned about this. I learned that I could write a total log. I could recover back to states that that were supposed to be consistent, but I didn't define what consistency meant. And this is one of these things that I don't see in the lectures about distributed systems and transactional systems and whatnot, is that we talk about the techniques, we talk about the log, we talk about consistency, but nobody ever actually says who defines consistency. And ultimately, it is the owner of the data that defines the consistency. I don't own that data. I'm the storage engine. I had another layer on top of me that was the metadata management engine of the file system itself, and it logically owned the definition of consistency. But then another layer on top of that had its own ideas. So we had what we called the anode layer, which was an inode, a data structure that described objects on disk. And then above that, we had another layer, because one of the things we did is we allowed multiple namespaces, rooted namespaces within a single logical block of storage. And we called these namespaces volumes. Actually, we ended up calling them file sets because volume was used for something else in DCE DFS, but we used to call them volumes in AFS3. It was the same idea. So we divorced the idea of a rooted tree from the partition where the rooted tree lived. And that was important functionality for us because it meant that we could then move that rooted tree to a different storage location without breaking anything. It was really cool. I actually worked on part of that implementation, and I alluded to this earlier when I foreshadowed oh yes, and delegation was very useful. So we actually had the ability to say, yo, that partition of that drive on that server is getting full. I'm going to move that file set to a different partition on a different server. And literally what would happen is we would create a what we call a clone. I think it was clone, maybe a snapshot. We would create a copy on write clone of the original file set. And that meant that anything that changed, any of those metadata structures that changed, would cause a new copy to be made. So we had these shadow copies. We had the copy at the time we created the clone. We had the changes to that, and so it was very space efficient. And when you wanted to move that set of files, what you'd do is you'd say clone, and then you'd say, okay, now move the copy of that clone over to the new location, and then you'd say now block all access to that file set and do an incremental backup and restore to the remote location. So we did it in multiple stages. We did this bulk copy operation without locking people out of using that storage space while we were moving the data. Does this sound complicated? Lots of interesting failure possibilities here for sure. We move that data to the new server. When the new server has the copy of the data as it was n minutes ago, whenever we made that snapshot, then we'd say, now we're going to block applications, and now we're going to move whatever data has changed since then. And then we get that incremental update done. And then we tell the client that it called, we'd say, you know what? We moved that file set. You have to go over there now. And so we would send it a redirect, and the client would say, oh, okay. And it would make an RPC over to the other server, and it would then proceed. From an applications perspective, it was absolutely wonderful. And this is one of the reasons we build distributed systems, because it means that we can provide these kinds of services in our back end that give us this really great functionality and don't break applications. You could literally be using that file and you probably wouldn't even notice that it got moved from location A to location B. That's the kind of functionality we're trying to build. That was why we chose to build a new physical media file system, to make it possible to realize this. We did some pretty extreme things in DCE, in DFS in general. So we had the backup restore stuff. So one of the interesting points about the backup restore stuff is that when I built the utility that actually moved those file sets in the way that I was just telling you about, and one of the things that was useful about having delegation is that instead of me saying, okay, Mr. File Server, give me all of this backup data for this file set so I can then write it over to this other file server, I could create a connection to each of the file servers, and I could say, okay, now I authorize you, the file server with the data, to directly send that data to the other file server. So I would cut the amount of network traffic in half. Another interesting challenge in building good distributed systems is minimizing your data movement. Moving data is expensive. If you can cut 50% of your data movement out, life is really, really good. So I've spent a career building these kinds of transactional systems and looking at ways that you can flex the definitions. You can meet specific consistency guidelines. So that whole thing about consistency, see, there's this idea of durability, but in fact, we found that what was more important to us was consistency than durability. We were willing to give up a small amount of durability for performance, but we weren't willing to compromise on consistency. So in other words, I could actually roll back to a consistent point that maybe there's some other consistent point that I might have been able to get back to, but I don't know. I mean, there was the system that I built actually is it was completely asynchronous, and it has tainted me. In all fairness, I like asynchronous programming. It has helped tremendously in understanding how distributed systems work and how to reason about things. The downside of asynchronous programming is that it makes it hard to reason about the order of events. That's going to be tomorrow's lecture. What is the order of events? And I can tell you, it has been really useful to break down that bias, to break down this assumption that I can look even at a single computer system and know the order in which things happened. For many, many, many years, I taught file systems development on Windows, and I have this one slide that I used for years. And I told people, I said, this is the slide that I present in order to convince you do not want to build a file system on Windows. You don't want to build a file system on any operating system, to be honest, but Windows was particularly challenging. And I would then point out that it was very common. It happens on Linux too. It's very common when you actually copy a file. It is quite possible, depending upon how the application that does the copy works, it is quite possible that an application that is copying a file will send the write to the destination file before it has read the data from the original file. In Windows, this happens because someone memory maps that file into the address space of the copy program, and then transfers the address of this virtual memory segment that hasn't been loaded off of disk yet to the file system. The file system then calls a function that says, okay, copy it from this buffer into this buffer. Well, since this buffer is a virtual address that doesn't have data in it because it hasn't been fetched from disk yet, what that causes is a page fault. So you literally see a write call to the destination file arrive, and then before that write finishes, you see a read call come in for the source file, and you're like, what? Why are you reading the source file after you started writing the destination file? Once you go through the explanation, people understand it a little bit better. Well, the same thing happens when you try to optimize the performance of storage. You see, if I'm talking to a drive, if I'm talking to an NVMe drive, a rotating media hard drive, which my computer right here is this insane monster with, I have three 12 terabyte hard drives and four solid state drives, all NVMe. I don't actually have any SATA SSDs in it right now. The hard drives are SATA, but not the SSDs. So they all work pretty much the same way, which is that I can send data to them, and it takes a while for that data to get moved from host memory onto the corresponding device and to be acknowledged back. Depending on the drive, it might just lie and say, oh yeah, I've copied it to persistent storage when it hasn't. This is an important consideration for people who build databases, for instance. They tended to prefer using SAS or SCSI devices because serial attached storage or small computer systems interface storage, SCSI or SCSI, they both relate to they provide high levels of performance, but they do it with a durability guarantee that once the drive tells you that it's written, it's actually on the drive. Cheaper drives tended to be willing to lie. Well, yeah, I wrote it. It's still in a piece of volatile memory, so if the power goes away, sorry, you lose your data. So the SATA interface actually has a command that says here's a command to flush the data to make sure that it's actually been committed to disk. And some of the drives actually do implement it, and some of them don't. It's a lot easier when you get to things like NVMe because they do have, while they have some volatile memory, they're just talking directly to their non-volatile memory. So they stage things in an intermediate fashion. They can provide much stronger guarantees because they are much more sensitive to some of these issues. But be that as it may, the point is that especially when you talk to something like a rotating hard drive, which was the predominant paradigm for a very long time, including in that time period in the early 1990s, what we wanted to do is we wanted to be able to queue up as much I/O as possible to that drive so that we could get better use of the drive. Many years ago, I remember working on I taught classes on building device drivers on Windows, which has a beautiful actual device driver environment where you can build highly portable, hardware portable device drivers. And so they have these nice models and these abstractions that are very thin, very efficient. So you teach people these rules about how you're supposed to deal with things in the driver, and then you actually look at at the time it was the ATA driver, and you actually look at how it was really implemented, and you go, excuse me, but you told me you're supposed to do this stuff in a deferred procedure call, but here you are, you're reprogramming the hardware inside of the interrupt service routine, and why is that? I thought you told me I shouldn't block the interrupt service routine any longer than absolutely necessary. And the answer is, well, yes, but sometimes we do things for performance. And so literally what would happen is that the interrupt service routine would pick the next item on the queue to be sent to the device, and it would reprogram it there. And the reason was because we didn't want any more idle time on that device than we could possibly get away with. And there wasn't any way of doing it faster. The device says, I'm done. And you say, okay, here's your next job. Not okay, thank you very much, and then kick the logic that will send the next job at some point, maybe even just a few milliseconds later. That time starts to add up. So we're building these things, and we build them very asynchronously. The whole system from the bottom to the top is built to be extraordinarily efficient. Asynchrony helps with that a lot. So I just said, it literally would take the next request out of the queue and pass it along. But if there wasn't another request in the queue, then it'll be like, okay, fine. Nothing to do, let the drive go idle, that's fine, not a problem. So in order to keep that drive busy spinning, what we would do is we'd make sure we had a queue. Well, how do you get a queue? Okay, well, you start putting blocks in there and you say, here are all the things I need to do. And then the driver can make a decision. It can say, all right, I'm going to reorder those blocks so I can get more optimal performance. Drives have been doing this for decades. There are lots of interesting challenges with rotating media that are still reflected in the I/O models of our operating systems because they had to deal with this. Fine. I had full asynchrony. I would asynchronously spool the log out. You didn't do synchronous writes to the log. You said, oh, this log block is full, queue it to the disk. Don't wait for it to finish. Start on the next log block. Oh, this block of data needs to be written, queue it to the disk. Don't wait for it to be written. The only reason you wouldn't write that log block is because it relied on something in the log having been committed to disk. And so you have these high watermarks, and you have to keep track of what's been committed and what's outstanding. So each time I wrote a new log block, I'd say, well, the last confirmation I got for anything in this log file, the last reliable confirmation is back here. And maybe it was 3 blocks back, maybe it was the block before, maybe it was 16 blocks back, who knows? I mean, the log is just this big, it's a flat buffer, but we think of it as a circular buffer where we just keep going around and around and around. Had to write all the code to handle that. Had to write all the code to handle what happens. So you keep a counter. Each time you go through it, you increment a counter. Had to write the code that said, okay, well, what do you do when the counter goes back to 0? You want to know a great trick? Initialize it to something just below 0, so you'll always be testing that path. That's not a distributed systems thing, but that is a systems thing. You have to expect, you need to write your code in a way that makes it easy for the very things that you are worried will not work right, will get tested. It goes wrong in systems all the time, and we can't afford that. So here we have this nice parallelism. We've got this nice asynchronous logging system. It has, I spent years literally building an entire checkpointing system where we would run our entire stack on a virtual drive, all in user mode because we were simulating it. It used this, it implemented exactly the same interface. I went through this code, I don't know, a couple of years ago, looking at it and going, wow, it's crazy. I would do a better job of writing it now, decades later, go figure. But it was still there, you know. So we had a disk that we had a disk that was just a file that implemented the interface that we expected to get from the Unix kernel. And every single time a write would come through, what I would do is I would stop and I would snapshot that, and then I would run recovery on it. I would run the log process, the post-crash log recovery. Why do you do that? Well, it's an extreme example of this, but the reason you do that is because now it means that you can literally check to make sure that no matter, as long as you have one block that changed, it won't lead you into a state where you can't recover back to a consistent point. Well, now this is where that point I was making before was, which is I didn't get to define consistency. Somebody at a layer above me got to define consistency, but I got to control the blocks. I got to control the order in which things got written out to the log. So if they screwed up their definition of consistency, oh crap, that should have been in the same transaction, it would break their stuff. My stuff was responsible for making sure that I could recover that log. So how do you recover the log? You go and you say, well, I don't know. Okay, so the log is this big. I'm going to look at the first block and the last block. And because remember, I've got a monotonically increasing sequence number there. So, and now I say, well, okay, these numbers are different. And now I'm going to look at the middle of the block, and then I'm going to figure out what I'm actually looking for. The head of the log, or the last entry I put in the log, is going to be either on the lower or the upper half. And then you just keep doing that binary search. So, and then you found that when you finally found that one block, you said, okay, this block said, I don't know about the state of these intervening blocks, but I know this block before was in fact completely recorded. So that at that point and everything earlier than that has been recorded in this log. So you'd say, oh, all right, so now I just have a little window, and I just read that little window until I made sure that I could find the most recent consistent point. That's why I said, you know, it's like, well, I might have partial data there. Maybe I could have restored something from that, but no. I'll pick the last block that the committed the committed range is in a range that I know is valid. And once I know that, that becomes the head of my log, and that's where I start my recovery. And then I would say, okay, so this recovery tells me that the tail of the log, i.e. the oldest live block in that log, was at some other location. And I would go to that other location, and then I would read everything between those 2 points. And then I would say, okay, now let's take all of the records out of them, take all of the undo records, all the things that I need to undo for any transaction that was not committed. Let's take all the redo records. Let's find all the commit records. Now I have everything I need. I apply all, I I literally would then sort them by block address, because it was very common for multiple operations to be on the same disk block. So then you'd sort them out. You'd pull the disk block, you'd apply all the undo records, undo, 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 undo. You'd apply all the redo records, redo, 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 and then you'd write the block out. And then you would test to make sure the drive was consistent. I mean, when I was testing it, that's what I would do. I would test to see if the drive was consistent at that point. And if it didn't work, then what we'd do is I would save a copy of that disk image, and then I would allow it to continue. Because the drive, I mean, the test harness really hadn't crashed yet. I had just taken an intermediate image, and we just ran that. There's several of us that ran that on our workstations all the time, continuously for years, literally. But that was the point I was making. I know it's kind of long-winded. You're probably getting used to that by now. A transactional system is easy to build and hard to get right. And that is actually what I'm trying to say in its long-winded kind of fashion. Why is that? Well, I told you I built a log. Building the log was the easy part. Defining what consistency was turns out to be the hard part. I had to do this little mock lecture for this class before they offered me the lecturer position. And they asked me to do replicated state machines. And so I was like, okay, well, I'm going to try and describe this in the way that I think about this. And I said, I know what a state machine is, and pull out a definition of a Turing machine, basically, and what they called accepting states in the Turing machine is what I refer to as distinguished states or consistency points. Rejecting states are anything in between. Now, if you twist it around like that, then you start to think of it, okay, so, all right. So the difference is that instead of a rejecting state, what I do is I say, and now I have this little extra bolt of data on the side that allows me to undo anything that I did from this rejecting state back to the previous accepting state, because I always want to start from an accepting state. Now I can reason about things. Now I can think about what's going to happen. So if you get to a point and you say, this is not an accepting state, then it's not a consistent point. It's not an acceptable place for me to restore the system. And this idea of having a known good state, a consistent state, is one that you see over and over again. I haven't worn that t-shirt yet. Oh, I didn't wear a graphic t-shirt. I just wore a little animal t-shirt today. And I've forgotten what I was going to say. I'll pull the t-shirt out at some point. The point is the accepting state, the consistent state here. Oh, it's the one about if I'm ever on life support, unplug me and plug me back in and see if that fixes things. And it's this idea that the reason we reboot computers is because we want to get back to a known good state, a consistent state. When we reboot the computer, we will start the operating system up from scratch. It'll load everything up from the disk, and life will be good. And when it's not, it's usually because there's something deeper wrong with the overall system. For example, I had this problem here. Like I said, I have this crazy system. I ended up rebuilding it last summer because I started having thermal issues. The processor was reporting only on reboots, but it was reporting that it was over temp, which is a little bit disconcerting because high-end processors generate a lot of heat. It is not a good thing to be ever being told that it's overheat, over temp, and over temp for this is 95 Celsius. So I was like, well, how could this possibly be? And I started really looking at it, and I'm like, I think maybe the cooler, which it only was just a year old, I think the cooler might be failing. And I was like, that seems kind of surprising to me. So then I spent a lot of time working on it, digging through things. I fixed the cooler. Well, actually, I kind of went overboard. I not only fixed the cooler, I fixed the cooler by converting from just an AIO, which is a single attached liquid cooling solution that pumps heat away from the CPU to um, a radiator with a set of fans on it. And then I went to a full water-cooled solution because I said I really started digging into it. I was having some other issues, and I was like, oh, maybe these are thermal related. And so I ended up putting a full water-cooled system. So the GPU and the CPU are now both thermally active. I now actively monitor the heat on the system. Let's see, I can go look right now. And the CPU, let's see, which of the 468 programs I have, here it is. The CPU at the moment is running 43 degrees Celsius, which is not bad. I'd like to keep it in the low 40s. I'm not overclocking it. I'm not doing anything really insane with it, but I'd like it to last a very, very long time. And the Windows Task Manager will actually show you the temperature on your GPU. I have an NVIDIA GeForce RTX 4090, which I recently installed, and it is currently running at 31 degrees Celsius, which is absurdly low for this processor. Actually, even my CPU running in the low 40s is absurdly low. It puts it in some of the coolest, like couple percentage points. People collect data on this stuff, which makes it easier to analyze. I've never seen my CPU. Well, I've never seen my GPU run above about 34. Now, I haven't really. I need to go get a copy of the portal that uses the ray tracing stuff and see if that'll drive it up a little bit. The CPU's been warmer since I switched to the 4090, but even so, it's still running in the low 40s, and I'm fine with that. So thermal issue actually caused damage to one of the NVMe drives, and I started looking at this NVMe drive, and I'm going, oh wow, it's reporting unrecoverable errors, and so then I ran it through that, and I forced a full media check, and it found even more. I was like, oh, this isn't good. When media starts to fail, it's time to replace it. And I was having problems with Windows, and so I ultimately replaced it. And I monitor that as well, although I haven't monitored in a little while. So I have the point, of course, being if you reboot your computer and it doesn't reboot, then it could be because there's actual damage to the hardware itself, and transactional systems aren't going to fix that for you. That's a failure mode that's probably outside of the threat model that we're considering. So at any rate, it is now just at the end of the hour. No one popped in as I suspected no one would. It's kind of normal for office hours at this point. I did get the drive thing back up. Let's see. Performance. It's not showing me anything quite yet, but oh, that's because it's not going to tell me that one. It should tell me that one. Usually it'll tell me what the temperature is if I pull up the Samsung test tool, but such is life. At any rate, it's not really very important. I do actually monitor the temperatures on these things now because I've learned heat is your enemy, and it can cause damage that we're not going to be able to fix with any transactional system. All right, well, for those of you who actually watch this, hopefully you'll enjoy it. If you don't watch it, then that's fine too. And I will hopefully I'll see you to some future office hours. Have a good one.